In this appendix video, we look at the geodesic equation. That is, how do we describe a straight line in arbitrary coordinates? At least that'll be our starting point. If we start with rectangular coordinates, say y1 and y2, and we draw a line, and then we measure position on that line as a function of distance from the start of the line, then the graphs of y1 of s and y2 of s will be straight lines. They will have no curvature. So their equations read y1 dot, that is the slope of the y1 curve, is a constant, and y2 dot is equal to a constant. And then they have no curvature, so y1 double dot is 0 and y2 double dot is 0. Those are the equations of lines in rectangular coordinates. Very simple. There's no curvature. Now we think of y1 and y2 being written as functions of some curved coordinates, x1 and x2. And we use our chain rule from the slope and curvature appendix video to work out the slope of y in terms of the slopes of the x's. So we have yi dot is y sub I comma j, the slope of the ith y coordinate with respect to the jth x coordinate, times xj dot, the slope of xj. Now the slope of that slope, that would be the curvature of yi double dot, which we know has to be equal to 0, we can get by taking the derivatives of each of those factors in turn. So we have the first term, y sub ij, times the derivative of the second, which is x double dot j, and then plus the second, that's your x dot j, times the derivative of the first. And again, we use the chain rule. So we have y sub I comma j k. That would be the derivative of y sub I with respect to j and then with respect to k, then times x hat sub k. So now that we've written our equations, that the rectangular coordinate plots have no curvature, but written those in terms of the curved coordinates, the x's, we're going to try to turn around and solve for the curvatures of the x coordinate plots. And that'll allow us to figure out how they evolve as we draw a straight line. So we'll go through a couple examples first and then work out the general case. Let's start off with polar coordinates. You have polar coordinates on the left, x1 and x2. So x1 increases along the green radial lines, x2 increases along the magenta circles, and corresponding rectangular coordinates y1 and y2. The specific relationships are that y1 is equal to x1 cosine x2, and y2 is equal to x1 sine x2. We can then use calculus to get the dy's. We'll show in just a minute how to use a computer to do this. So we get our dy1 and our dy2. And then using the convenient fact that cosine squared plus sine squared is equal to 1, we end up with our expression for our ds squared, for our Pythagorean theorem. dy1 squared plus dy2 squared, we'll see is dx1 squared plus x1 squared times dx2 squared. So from that, we can directly read off the metric coefficients. There's 1 for g11, and there's x1 squared for g22, and there's no g12 or g21 term. Then we'll see we can directly, with the computer, solve for the curvatures of the x1 and x2 coordinates. So here we are on the computer. I'm using an open source piece of software, a computer algebra system called Maxima. There's a link to the download in the description box. And the blue entries here are what I type in, and all the other stuff is what the computer spits out. So first I say, I have coordinates x, and they depend on s. So I say depends x on s. Then I give the expressions for the rectangular coordinates in terms of the polar coordinates. y1 is colon x1 times cosine x2, and the same for y2. Now I simply tell the computer to work out the Pythagorean theorem. The differential of y1, that's your dy1, squared plus the differential of y2 squared gives me that expression, does the calculus, and I see some trig functions in there. I tell it to do trigonometric simplification, and we end up then with our del x1 or dx1 squared plus x1 squared dx2 squared. Okay, so now we just write out that the curvature of the y1 coordinate is 0. So I'm going to say equation 1 colon, so this is, I give a name to that equation. The derivative of y1 with respect to x, two derivatives, so that's the 2, is equal to 0. Okay, and it does the calculus and writes that out. I just put the blue stuff in. But equation 2 is that the derivative of y2 with respect to x, two derivatives, is equal to 0. Again, the black stuff all comes out of the computer. I then tell Maxima to solve the two equations, equation 1 and equation 2, for the derivative of x1 with respect to s, two derivatives, second derivative, and the derivative of x2 with respect to s. And it spits out the solutions. There's my x1 double dot, or second derivative of x1 with respect to s squared. It's x1 times the square of x2 dot, And the x2 double dot is minus 2x1 dot x2 dot over x1. That's where those equations came from. So now I'm going to tell the computer to just select some random values for x1 and x2 and some random directions to start off in, and then just to solve those equations that we just got numerically. So here it goes, and supposedly all these red curves are lines, and in fact, they are. Back in the real world, what's going on here is that we're looking at the x1 and x2, the polar coordinates, in a rectangular format. Indeed, if we distort the plot back into the format we know it has in the, quote, real world, we see that we indeed do get lines. In fact, if we just simply plotted the solutions in that proper format, so to speak, we would directly have gotten lines in the first place. But this brings up an important point that's relevant to relativity. Those two different formats, those two different ways to view the same solutions to those equations are indeed the same. We're just looking at them from different points of view. And that's what happens in relativity when you use different frames of reference. You're looking at reality from different points of view. It corresponds to the same reality, but it will look different. Now, this approach of referring things to rectangular coordinates actually won't work when we have a truly curved space. So we ask, can we do this whole process without referring to rectangular coordinates? So we start off with our original equation that the rectangular coordinate plots have no curvature. And we use the result from the appendix video on the metric coefficients that relates the metric coefficients to the derivatives or slopes of those rectangular coordinates. We rewrite the first equation and then notice that if we multiply by the right factor, we can get something over on the left that looks like a metric coefficient. The y product on the right isn't quite a metric coefficient because it's got y sub I comma j k. It's got two derivatives, but we expect that we might be able to get that if we take derivatives of the metric coefficients. So we use our chain rule on our g, j, k expression, cycle through the indices. Again, this all looks complicated, but we're going to let the computer actually do the hard work. See that we get a lot of similar terms. So if we took these three equations here and appropriately subtracted them, we might end up with something that looks just like our y product in our equation that we're trying to simplify. So putting these together, we can get an expression for that y sub I comma L, y sub I comma jk in terms of the metric coefficients. Okay, that was relatively complicated, but in fact, it's just a lot of messy algebra with a little bit of our chain rule calculus thrown in. So now we can substitute in for the y terms in our original expression, and we end up with an equation that has only the metric coefficients and the x coordinates. There's no reference to the rectangular coordinates. Now we're not quite done yet because over on the left, what we actually have is g sub L j x double dot sub j. That's a sum of a bunch of terms. We want to solve for just one of the x double dots. So one more step, matrices have things called inverses. When you multiply them together, you basically get 1. So we multiply by the inverse of that g sub Lj, and we end up with the desired result, x double dot sub I. So this is the curvature of the ith coordinate as a function of distance traveled along the path is equal to something over on the right that involves the metric tensor and its inverse and the derivatives and so on, all that stuff that can be calculated in the computer, and then the slopes of the x coordinates. That expression over on the right with involving the g's is very important, comes up a lot. We give it the symbol gamma. It's called the Christoffel symbol. Gamma superscript I subscript jk is that expression there. These are also called the connection coefficients. They're the equations that tell us how to draw geodesics, or minimum length paths. Straight lines in flat space, geodesics in curved space. Okay, that was all a big mess, but we only have to do it once and for all. And now we can go into the computer and we can let the computer do the hard work. So here again, we have maxima. The blue expressions are things that I type in. Everything else comes out of the computer. So here I tell it the metric coefficients. G is a matrix with, in this case, this is for our polar coordinates. The metric coefficients are 1, 0, 0, x1 squared. So maxima figures out the size of my space. In this case, it's 2 dimensions. I tell it to find the inverse of that metric tensor of that matrix and display it. And there you see the inverse matrix. It just has 1 over x1 squared, literally the inverse of the corresponding term above. Now we put in all that mess we had for the Christoffel symbols. Looks a little complicated, actually fairly straightforward. We're just stepping through I, 1 through n, etc. Maxima spits out the answer. The gamma 1 jk matrix corresponds to the curvature equation for x1 and the gamma 2jk matrix curvature equation for the x2 coordinate. Now we want to look at the case where we have a truly curved space. We're going to look at an n-dimensional curved space that's embedded in a higher dimensional flat space. And our question now is, what does our geodesic equation produce? We know that in a flat space it produces lines. To be specific, we'll look at spherical coordinates where we have two coordinates x that are the angles, basically longitude and latitude, that position us on the surface of the sphere. And of course that exists in a flat three-dimensional space that has three rectangular coordinates like x, y, and z, or we call them y1, y2, and y3. So we need to get our metric, so we go in and just put the equations in for y1, 2, and 3 in terms of the x's, and tell Maxima to do the Pythagorean theorem in the rectangular coordinates, but work it out in terms of the curved coordinates. We end up finally with our metric is dx1 squared plus sine x1 squared dx2 squared. Very similar to the polar coordinates, but now instead of x1 squared, we have sine x1 squared. So we go back and just change our metric tensor. The x1 squared term becomes sine x1 squared, just rerun everything, and we end up with our equations for the curvature of the x1 and x2 coordinates. Now they have these trig functions, otherwise they're somewhat similar to what we had before. So we now take these and numerically just pick random points in the x1, x2 space, that is random longitude, latitudes, random directions to start off in, and just tell the computer to numerically solve these equations and plot the results. What we get don't look like straight lines. Remember, this is now curves in longitude and latitude. So what are these? Well, if we plot the same solutions in three-dimensional flat space, what we see is that these are circles on a sphere. In fact, they're great circles. They're circles whose center is the center of the sphere. Those are geodesics on a spherical curved surface. So we see that the geodesic equation that we presented in video 7b draws straight lines if we're in flat space, and if we're in curved space, it draws geodesics. By the way, I just want to point out that if you're willing to do more math, you can show that any path satisfying this equation is indeed the shortest path between its endpoints. And actually, this geodesic equation is a special case of something more general. If you go to any point in your space and you draw any vector, any arrow pointing in some direction, and then move the base of that arrow a little displacement dx while keeping the arrow parallel to itself, at least what you think is parallel in your space, you find that the components of that vector will change by some dw. And those dw are given by an equation that looks very much like the geodesic equation. It says dwi is minus gamma ijk wj dxk. But now the vector w is not necessarily the tangent vector, the vector in the direction you're moving. It's an arbitrary vector. And so the geodesic equation is actually a special case of the equation for parallel propagation of a vector. So to follow a geodesic just means you keep parallel propagating or moving in parallel your direction vector, your heading, and that kind of makes intuitive sense.